Hey guys, this is Valdivia here, and today we're going to be going over Chapter 11, Solutions, and describing our concentrations using solutions. So, first of all, what is a solution? Well, a solution is basically a homogeneous mixture, and that means that your solid has been nicely dispersed throughout your entire solvent, right? So let's take a look at what I mean about that. Um, So, describing our solutions, okay, we want to be able to take some particles and dissolve them inside a solvent. Now, a solute and a solvent, and let's go ahead and describe the difference between both of them. A solvent is what does the dissolving. So, in this case, I'm having an example of Kool-Aid and water. So, here is my water, H2O. And so my water is going to dissolve my Kool-Aid. So therefore my water is the solvent, and my Kool-Aid, which is what is getting dissolved, is going to be the solute. Okay. And together they're going to create a concentrated solution. So now I'm going to have a nice little solution. Okay. And in this case, my solution is all going to be very nicely dispersed throughout. Now let's go ahead and write down what our solution is so we don't forget. So a solution is any homogeneous mixture which basically means your solute has dispersed throughout. So this means your solute has dispersed throughout the solvent. Okay, so it's like kind of like a perfect union. Every single water molecule now has some solute inside of it. Now, what if we were to take our solution, our new concentrated solution, and add some ice to it? So we have our new concentrated solution. I'm going to use this color pencil to do this with. And we added ice. All right. Oh, sorry, right over here. So we added ice. And now, tons of ice to it. Ice everywhere to our solution. What this ends up doing is it increases the volume of our solution. And the way that it increases the volume of the solution is not because we added more solution, we added more solvent. Right? I'm just going to make this the same here as the other one. All right, so we added more solvent. And now we can see that in this case, our concentrated solution is a nice deep purple color. And this is the same concentrated solution, and we added some ice to it. And now we have more of it, right? And it's in a lighter shade of color. What ends up happening is that we diluted our concentrated solution. And to have this diluted solution means we have more solvent. Okay, more solvent. And we could potentially add more solute. So more solvent in this diluted solution. Same number, so it's the same amount of solute. So that does not change. We did not take away solute. We cannot take away solute at all. So we have the same number of solute, just more solvent. All right, now let's say we're like, oh my goodness, we didn't like that diluted solution, right? We're like, whew, what can we do to help out this diluted solution? So here's my diluted solution, right? The ice is all melted in it, so now I just have tons of diluted solution. And I'm going to add Kool-Aid packets, but this time I'm going to add 2 Kool-Aid packets, right? 2 Kool-Aid packets to this solution. Well, what ends up happening is that now I'm going to have this solution, and I'm going to have tons of Kool-Aid that collects here at the bottom, right? All that sugar from the Kool-Aid, basically, because we all know Kool-Aid is just sugar with food coloring and artificial flavoring. All right, so here it is. Tons of this was left here at the bottom, right? And the rest of it is just our solution, bit darker color, right? Because it's very concentrated. So what do we call this down here? Well, this is now known as saturated. Okay, so it's actually overly saturated in this case. There's actually a word for that. It's not coming to my mind right now, because saturated is when you have every water molecule has a sugar molecule attached to it. In this case, we have over that, right? It's overly saturated, and this is what's left out. It's seeping out of the water, right? So in this case, we have more solute than solvent. All right, too much solute, not enough solvent, and we created a saturated solution by adding too much of our solute to this one. All right, so hopefully we're able to describe really quickly what a solution is. It's any homogeneous mixture solute that has dispersed throughout the solvent, and it's made from a solvent plus a solute, and you can make a concentrated solution. This concentrated solution, if you add more solvent, right? If you add more solvent, then you're going to create a diluted solution. And if you take your solution and you add more solute to it, then you're going to create a saturated solution. Okay, so those are the quick little ways of describing concentration. And now we're going to describe this concentration in the form of numbers, right? So quantities. Now, there's 3 different ways to describe it. We could describe it as a percent, we could describe it as a fraction, and we could describe it as molarity. So let's go ahead and start. So the first one is percent by mass and volume, right? So the mass percent is basically grams over grams. Grams of your solute divided by grams of your solution, or maybe you have kilograms of solute divided over kilograms of solution. Either way. So let's look at an example of that one. You add 20 grams of salt to 500 milliliters of water. Well, how do you find the mass percent of your sodium chloride salt? Well, we have the mass of the solute is given to us as 20 grams, right? And this is the mass of the solvent, not of the solution. So the mass of the solution is what we have to find first. So mass of solution. And that's going to equal to 500 plus 20, which gives us 520 grams of solution. Now we can go ahead and do the math. So we're going to take our 20 grams of our solute, which is the salt, and we're going to divide that by the 520 grams of our solution and multiply it by 100 because we're looking at a percentage. So we take our trusty dandy calculator, we have 20 divided by 520, and that gives me 0.038. I'm going to multiply that by 100, and I get 3.85% mass over mass of sodium chloride inside of the solution. Right, so it's mass per mass. So it's actually very simple, right? It's the part over the whole. You just have to make sure, the tricky thing is that you're taking the mass of the solution, not the mass of the solvent. So you do that by adding them together. All right, let's take a look at the next one, which is volume percent. So in volume percent, what we're going to use is we're going to use an example of bleach that's given to us here. So it says a clean solution contains about 2% of ammonia in water. what volume of ammonia is needed to prepare 10 liters of this solution. Right? So we want to prepare 10 liters of the solution. That's the volume. And we're actually given the percent already, the 2% of ammonia inside of water. So we are given 2% is equal to the volume of the solute, which I'm just going to put as X, divided by the volume of the solution, which is 10 liters. Okay, so this information is given to us, and now we could go ahead and solve for this. If we remember, a percent is a number over 100, right? Because we had to multiply it by 100 to get to this. So all I have to do to this is divide it by 100 and take it out of the percentage. So I'm going to take 2 divided by 100, and I get 0.02, and that is equal to X over 10 liters. So I'm going to divide by 100. And now I need to isolate X, so I'm going to multiply both sides by 10. 10 goes away. And I am left with 0.2. Okay, and that is the volume of my solute, and I'm pretty sure this volume is going to be in liters. Okay, so let's take a look at this. Okay, so the volume of the solute is 0.2 liters. And we solve this by using the volume percent, okay, of our cleaning solution. Now let's take a look at another one. Right? Oh, and it converted it to milliliters. Did it say it wanted it in milliliters? It didn't. But if we were to convert it into milliliters, it's 200 milliliters. All right. So now the next one we're going to look at is mass divided by volume. Okay. So the mass of the solute divided by the volume of the solution. And as you guessed it, it's going to be quite the same. It's just grams per milliliter as our unit. So I'm going to write that down. That's important to know. It's grams per milliliter is our unit. Okay, that's our unit. And we describe this as percent of M over V. This one was described as percent of V over V, and this one was M over M. Okay, the percent of each. All right. So if we look at sodium chloride inside of those solutions that they give us, when we're dehydrated, right, a saline solution, we have 0.9%, right? That's what it's made out of, 0.9% of salt inside of your saline solution. And we want to know, well, how much saline, how much of your salt is that actually giving you? Well, 0.9%, it's a number over 100, right? So if you take that number, you're going to have 0.9 grams over 100 milliliters, right, of your solution. So it's just the number over 100, 0.9 over 100 milliliters of solution. So that's actually kind of easy to break it down. Let's go ahead and look at another example for this. Okay. Oh, actually, even before we do that, let's talk about saline really quick in this. So the saline that they put inside of our body, 0.9%, right, when we're dehydrated. The ocean has a saline value of about 3.5%, and Death Valley has a saline value of about 34%. So that is very, very salty. All right, now in this example, we have normal saline solution is about 0.9% sodium chloride. How many grams of sodium chloride are needed to prepare a 0.50 liter of normal saline? So when we set up the problem, it already gives us the percentage. So just like this one, it gives us the percentage. So we're at 0.90%. And that is going to equal to the mass of the solute, which we don't know. So we have no idea what this number is. And that's going to be in grams. Divided by our solution. And it gives us 0.50 liters of our solution. Now, one of the things that we learned in the previous slide is that the unit has to be in grams per milliliter. So therefore, we're going to have to convert our 0.5 liters into milliliters. So I'm going to do that conversion right over here, 0.5 liters. Okay, and there is 1,000 milliliters in 1 liter. Liters cancel out, and I'm going to take my 0.5 and multiply that by 1,000, and I get 500 milliliters. Okay, so I'm going to have 500 milliliters here. All right, so now we could go ahead and continue to solve our problem. Now, just to show us some of the steps, remember, this number is a number over 100. So our next step is to take that 0.9, and it's going to be 0.9 grams over 100 milliliters. And that's going to equal X over 500 milliliters. Oh, well, they didn't do the 500 milliliters. And let's see what we actually get when we start isolating this. So we have 0.9 divided by 100 multiplied by 500, and I get 4.5. So I multiplied it by 500 because I'm isolating my X. So I'm multiplying both sides by 500 milliliters. So milliliters cancels out, that cancels out. When we do our mathematics, we get 4.5 grams of sodium chloride. All right, so same difference, just a different way of showing how to do the problem. So our problem, in this one, they did cross multiplication, which is very similar to what we did. We just kind of cross multiplied, I guess. All right. So very dilute solutions are made out of, well, are not made out of, are described in parts per million and parts per billion. Okay, so this is for very dilute solutions. And when we talk about very dilute solutions, you could start thinking about the contamination of our natural resource water, right? Our waters have been contaminated by a lot of different plastics and trash and whatnot. And there is certain amount of this when it gets filtered. So a certain amount of that contamination of like a PBAs or something that is actually allowed in our drinking water. And the amount that's allowed is in parts per million or parts per billion. Okay. So, this is PCBs, polychlorinated biphenyls. Okay. And then the maximum allowed concentration, they say, is 5 times 10 to the negative 4 milligrams per liter. Okay, so that's the number of milligrams per liter. So the water that we actually drink isn't that pure because it has some sort of allowable quantities in it. All right, so parts per million, ppm, and parts per billion is ppb. So parts per million is described as times 10 to the x, or 1 million. So we're multiplying something by 1 million, right? And it's basically the same as everything else. It's just your mass of solute divided by the mass of solution times 10 to the 6. So instead of times 100, you're multiplying it by a million this time. Your parts per billion is exactly the same as well. You have your mass of solute divided by your mass of solution times 1 billion. So that's 10 to the 9. Now, the biggest difference that's going to be in here is the units of concentration. Okay, so the units of parts per billion is going to be 1 milligram per liter. And the units of parts per billion is going to be 1 microgram per liter. Okay, so it's actually a smaller unit per liter. Now, the other thing it wants us to know is the mass of 1 liter is equal to 1 kilogram. So we're going to write down water here, pure water. So 1 liter is equal to 1 kilogram of water. And 1 milliliter is equal to 1 gram. of water. So it's an equivalency. And how do we know this? We know this because the density of water is equal to 1 gram per 1 milliliter. Okay. So we could say they're basically equal to each other. So that's our density of water, is just 1 gram per milliliter. All right, let's go ahead and look at this example. It says, in a recent study, scientists found that samples from a European wastewater treatment plant contained 45 micrograms of phthalate, can't say that word, per liter of solution. What is the concentration in parts per million and in parts per billion? Assume the density of the solution is the same as pure water at 4 degrees Celsius, which aka means 1 gram per milliliter. All right. So the solute is 45 micrograms. Now, they wrote this in incorrect way of writing scientific notation. They just basically did it in exponential notation. And the reason they wrote this in this exponential, oh my goodness, I'm having a hard time with words today. All right, so they wrote it in the exponent format as 10 to the negative 6 is because it makes the other calculations easy, especially when it comes to parts per million. So let's go ahead and look at our solvent. Our solvent is 1 liter, which basically means 1,000 grams. So our ppm is going to equal to 45 times 10 to the negative 6 grams divided by 1,000 times 10 to the 6. Now, why does that make it easy? Well, if we were to look at a little bit of our mathematics, so I'm going to put a little line here. Okay. If we remember exponents, if we have 10 to the m times 10 to the n, that's the same as 10 to the m plus n. And I'll show you this other one too. 10 to the m divided by 10 to the n is the same as 10 to the m minus n. And that's for your exponents. So in this case, we have a 45 times 10 to the negative 6, right? And this is being multiplied by 10 to the 6th power. And it's divided by 1,000. So if I have 10 to the 6 times 10 to the 6, that's the same as saying 10 to the negative 6 plus positive 6. Okay, so hopefully you guys are following me with this. So negative 6 plus positive 6 is just going to equal to 0, which gives me 45 divided by 1,000. Okay? And when you do that math, you get 0.045. And that's easily counted by moving this understood decimal over 3 times because you have 3 zeros. So you go 1, 2, 3, and you end up with 0.45 parts per million, ppm. If you were to convert it in proper scientific notation, you still get the same exact answer. Same exact answer. The math isn't just as obvious as it is here, but you could still apply the same principle, because if you did it the other way, this would be 10 to the negative 5, right? Which would give you a positive 1 over here, and then you would still bring it over and do your math, and you'll still get the same number. Right. To calculate the parts per billion, okay, same principle. Instead of multiplying it by 10 to the 6, we're going to multiply it by 10 to the 9. So if I get that 45 times 10 to the negative 6 times 10 to the 9, right? I'm going to take negative 6 and 9. So using my little hands here, take 6 away. That gives me a 3. So all of that divided by 1,000. So I'm left with 45 times 10 to the 3rd over 1,000, right? Now, 10 to the 3rd is the same as 1,000, so we're going to be left with 45 parts per billion. Okay. So a quick little little summary on this part, actually, before we move on to the other one, is that our concentrations can be calculated using mass percent, volume percent, mass per volume, and they can be identified with parts per million and parts per billion. The next part that we'll be describing in concentration is going to be molarity, and I'm actually going to put that in a different video for you guys. Ciao!